I will do my best to keep track of what's happening in the chat. The folks who are on the HEC-FDA team, I would appreciate if you could help me track any questions that come up in the chat. All right, folks, let's get started. So welcome to the HEC-FDA quarterly webinar. This webinar, we're going to talk about frequency functions. Briefly on this title slide, you've got that familiar image on the top right. That's our HEC-FDA version 1. Bottom right-hand side, you're getting a sneak preview of what HEC-FDA version 2.0 will look like. We've got our HEC-FDA team listed here. I am the lead, Richard Nugent, and Leah Adams, Brennan Beam, Will Lehman, Jordan Lucas, and Julia Slaughter make up the rest of our really great team that we have here supporting HEC-FDA. So let's get into frequency functions. Before we get into frequency functions and all of the supporting content, let's talk for a minute about why we're even talking about frequency functions. So we know with pretty high confidence that uncertainty in expected annual damage, the distribution rather of expected annual damage and its mean are really dependent or really sensitive to the uncertainty in hydrology and also to some extent the uncertainty in hydraulics. So we want to spend time on talking about the best way to characterize that uncertainty in hydrology and hydraulics so that we can get the distribution of expected annual damage right. Right. So that's our goal today, is to better understand how hydrology and hydraulics affect expected annual damage, and in particular the uncertainty around hydrology and hydraulics, how that affects expected annual damage, the distribution. All right, so before we jump into frequency functions, because we're going to spend plenty of time discussing the uncertainty around these things and how they play into calculating expected annual damage, I just want to do a refresher on risk assessment with HEC-FDA. All right, this is going to be just a few slides real quick. If you'd like to get into greater detail, I listed a couple of resources here. The links to the YouTube playlist for our Prospect 209 course content, among other videos, is there on that slide. We have the online course content for Prospect 209, and then of course the engineering manual 1110-2-1619, which outlines the methods we're going to discuss today. These links are live in the slides that I've shared with you in the calendar invite. All right, so let's remind ourselves, what is flood risk? So risk is a function of the hazard, the performance, exposure, vulnerability, and consequences. Right? We're going to look at the hazard, which tells us what can cause harm. And in this case, we're typically looking at a channel, water, right? We'll include performance, which describes how the system reacts. So what is the probability that a levee fails, given that the channel stage is at a certain stage? We'll look at exposure, so who and what are in harm's way. Vulnerability, how susceptible are those in harm's way to being damaged? And then we'll look at how much harm could occur, which is a function itself of exposure and vulnerability. So we want to characterize risk, right? We want to quantify risk, which is the function of these things that you see on the screen. And that's what FDA does, right? We measure risk using expected annual damage. We're thinking about economic risk here. So we measure risk using expected annual damage. HEC-FDA calculates that. And so how do we get these different pieces of the risk formula modeled so that we can quantitatively assess risk? Well, we include information on the hydrology, which focuses on the water in the watershed. We need a summary relationship that describes the amount of water, the rate of flow, and the frequency with which we see that rate of flow. We need a summary relationship of the hydraulics. So we're thinking about the water in the channel or the floodplain, And in particular, we're interested in the elevation or the depth of water for a given rate of flow and the velocity. So in those two pieces, the hydrology, hydraulics, that makes up the hazard. Geotech focuses on levee performance, and to simplify things, for us today, I'm going to set aside the geotechnical part of the risk equation. And then we get to economics. We need a summary relationship that focuses on the stuff in the floodplain, right? So the value of the assets, the number of the people in the floodplain, that's going to tell us about exposure. First floor elevations, number of stories, that will tell us about vulnerability. And then C, damage, life loss for a given flood magnitude is a function of A and B, and we can also assess indirect economic impact. So we need this fourth relationship, which describes exposure, vulnerability, and consequences. And in FDA, we do that using, so diagrammatically here, a method that brings together the hydrology summary relationship, the hydraulic summary relationship, and the economic summary relationship. So what we have in the top right-hand side, that's our flow frequency function with uncertainty. The most likely flow frequency function is the solid line, and we have confidence limits in the between the dashed lines. Same thing, so that's hydrology, upper right-hand side, flow frequency, upper left-hand side, we've got flow stage. That's the hydraulic summary relationship that tells us what the stage in the channel is for a given flow. And we have uncertainty about that one too, that is characterized by those dashed lines. Bottom left-hand side, we have the economic summary relationship. What is the level of damage for a given stage? And what we're going to do is sample one realization of each relationship. We're going to combine them so that we can take a given flow to tell us what the stage is. From that stage, what is the damage? That damage tells us, and by combining those three, we get a level of damage that has a given probability of being exceeded in any given year. All right, we have the damage exceedance function, the bottom right-hand side, which we integrate, and that gives us a realization of expected annual damage. Because this is the FDA method. We could say in principle, the FDA method. We get into more detail about the FDA method in the prospect content that you can access online. I know that I kind of jumped through this real quick. I just wanted to set the scene. So we're talking about curve sampling, and we're talking about curve combination. And the way I want to talk about curve combination today is actually in terms of curve composition. And I'm hoping for the economists on the call, what you see on the screen here, I hope that it looks familiar to you, right? So if we have two functions, y equals f of x and x equals g of z, we can compose f of g so that y equals f of g of z, which is h of z. So really what we're doing when we're saying we're combining curves, we are composing one curve of another so that we can get a relationship between the two variables of interest, which is damage and frequency. So why am I bringing this up? Well, it can be helpful to think about this. Let's look at the first curve composition that we would want to do, right? Which is going to be between the flow frequency and the flow stage. We want to reflect flow stage as a function of flow frequency so that we can get to a stage frequency relationship. And then we'll compose the stage damage relationship with the stage frequency relationship that gets us the damage frequency relationship. All right, so that first composition, we're going to have flow frequency. Flow is a function of frequency, and then stage flow, where stage is a function of flow. Now, ultimately, we want to get to that stage frequency so that we can use stage frequency to describe damage frequency with the stage damage function. So we're going to plug in the function of frequency that gives us flow into the flow location of the function for stage, right? And we can simplify that expression so that we have stage as a function of frequency. Let's so what we see here is what we described earlier. We are combining or composing the flow stage function with the flow frequency function. That gets us a stage frequency function. Then we'll compose the stage damage function with the stage frequency, and that gets us the damage frequency. Okay, so once we've done that, we will do that many, many times. Here's our first realization from the previous slide, right? Damage frequency in the right-hand side is now plotted on the bottom left-hand plot. And we continue sampling and composing the functions again and again until we get convergence in mean expected annual damage. All right, so that is the brief summary of what we're doing with HEC-FDA. And we're going to spend more time talking about the role that curve composition plays. And it is especially useful to think about when we're thinking about whether we want to include a flow frequency function or if we're going to jump right to flow stage. Okay, so our objective all along is going to be to estimate expected annual damage, which is that integral of the damage frequency function. To develop the damage frequency function, we have to compose stage damage with stage frequency. And we have two options for getting to that stage frequency. Option one, which you see on this screen, is to compose a stage flow function with a flow frequency so that you get to a stage frequency. And we see that the composition of the functions in this diagram, where we have a flow frequency, is the first function, then stage flow, then stage damage, which gets us to frequency damage. And you can see that we're matching up the flows so that we can match frequency to stage. And then we'll do the same thing with stage. Ultimately, we'll have a relationship that reflects frequency, which you see all the way on the left-hand side of the first set of tables, damage on the right-hand side. That collapses. We collapse flow and stage to get us that damage frequency. So you can think of this as curve combination. You can think of this as curve composition, whichever your brain likes to use the most. So that's your first option. The second option is just to start with stage frequency, right? So you might ask, if we can just start with stage frequency, why include these two extra relationships if we can simplify that relationship down to one in our risk assessment? Well, that's the whole point of this webinar. Why not just start with the simplified relationship? We're going to talk quite a bit about that today. And let's skip that slide. So rather, let's not. Let's not skip that. Excuse me. So when we are carrying out option one, we're going to sample a flow frequency function. We're going to sample a stage flow function to get that stage frequency function, right? That's option one. So what you see here on this slide is what's happening in this diagram. And what's happening in this diagram is that we are including uncertainty in flow in the uncertainty of the damage frequency function, right? Because that top right hand, the top right hand side figure, we see a flow frequency function that has been sampled. So if we start with flow frequency and then include a summary relationship for hydraulics separately, we can include the uncertainty in flow separately from the uncertainty in stage, which is really what we want to do as long as we can model these two pieces of the risk equation separately. Okay, if we jump right to the stage frequency, then what we're doing is we're ignoring the uncertainty in flow. So I just want to emphasize that piece. If we go with option 2, so we're not going to start with flow frequency and stage flow. We go straight to stage frequency. We are now, in effect, ignoring uncertainty in flow. And so you can think about this as using the most likely flow frequency function for each iteration, right? Because we're not really reflecting uncertainty in flow. So then we can look at this distribution of damage here and ask, does this distribution reflect uncertainty in flow? Well, if you started with option 1 and you used a flow frequency function and a rating function, then yes, we have incorporated uncertainty in flow. If we go right to stage frequency, then this distribution of expected annual damage, what you see on the right-hand side, that orange histogram, then that would have assumed away uncertainty in flow. And so that is a, let's say, an acceptable method if there is no way to model the hazard other than stage frequency, if we're using summary relationships. Otherwise, we really want to reflect uncertainty in flow and uncertainty in risk. So when is stage frequency justified? When can we go right to option 2? There are two big reasons when we want to go straight to stage frequency and ignore or set aside uncertainty in flow. And that's when stage to flow is not one-to-one, right? What do we mean by one-to-one? So think about this, any of these functions. Let's look at the stage flow function because that's the one we're talking about. We need that to be one-to-one. In other words, if you took a pencil and you ran that pencil horizontally up and down the function, the pencil should cross the function just once so that there's one stage for a given flow and vice versa. That's what we mean by one-to-one. But if that's not the case, then it's really hard for us to include that the hydraulics in a summary relationship, and we would need a more complex risk engine than what we're using in HEC-FDA. So let's talk about a situation where the hydraulics cannot be summarized in a one-to-one relationship. And the most common situation is backwater, or perhaps tidal conditions or ice jam floods. So what's going on here in this image on the right is a situation where we may have some backwater, okay? So the image on the right-hand side, that's satellite imagery of the confluence of the American River with the Sacramento River. The American River is a darker color on the right-hand side, while the Sacramento River is the lighter color on the left-hand side of the image. And you can see that in this at this point, or on this day, the Sacramento River is dominating the flow at the confluence. As the flood magnitude increases on the Sacramento River, if the flows on the American are being held constant, what we can see is that the stages in the American will not change much as flows are coming into that confluence, because what you have there is sort of a ponding situation. So even if the flows from the American River are increasing a bit, the stage is going to stay about the same because it's like a pond. And so you've not that one-to-one relationship because you have flows increasing but stages staying the same, because the stage in that confluence is being dominated by the Sacramento River. So that's a good situation where we would want to just go right to stage frequency. Tidal conditions, also very common. The only other situation where we go right to stage frequency and we set aside uncertainty in flow is when stage is the only available gauge data. All right. So this is one of the biggest points that I wanted to make. Does anybody have any questions? Brian, I see your question, and I'll get to that. Folks, If anybody in the webinar would like to take themselves off mute, talk about this. Perhaps I said something wrong and there are engineers in the audience who could fix my discussion. I welcome that as well. So Brian Maestri asks, can the terms frequency and probability be used interchangeably? Brian, I think that I want to say yes, but we would want to be specific about the measure of probability, whether we're thinking about exceedance probability or non-exceedance probability. And I think that in our realm, frequency is often used interchangeably with exceedance probability. And then Andrew points out regulated versus unregulated mechanisms. So compounded uncertainties are rarely understood with the simplified notion that there's an exact stage for each flow coordinate to describe the system. That's a really good point. And we're going to have a chance to touch on regulated versus unregulated systems later in the webinar. Any other questions or comments about when stage frequency is justified and why we should try to avoid using stage frequency if we're not in one of the situations on this slide? And Brian points out that NVN uses stage frequency as inputs for your coastal evaluations, which is a totally justified situation, right? Because you've got tidal conditions. And so you're not going to be able to reflect the hydraulics relationship as a one-to-one function. And so you sort of have to go straight to the stage frequency. Any other questions or comments? Are we ready to continue on with our webinar? All right, let's do it. So let's now assume that we can start with a flow frequency function, that we can model the hydraulics in a summary relationship that's a one-to-one function. So we're going to start our assessment with a flow frequency function. Now we can ask, do we want to use an analytical flow frequency function or a graphical flow frequency function? So these are your two options when we're thinking about flow frequency. And note that if we went straight to stage frequency, that's going to be a graphical frequency function too. But here we're assuming that we can include flow frequency and stage flow separately in our risk assessment. And so we have these two options for a flow frequency function. And recall that our flow frequency here, we're looking at a relationship between a flow magnitude Q and the probability P of that flow magnitude being exceeded in a given year. So that probability P is an exceedance probability. And the flow frequency function is necessary to get to the damage frequency function. So really, our ultimate relationship that we integrate is an inverse cumulative probability distribution. And so we need to start with some probability distribution to begin with to get that concluding probability distribution. So there are two possibilities for that distribution. We can use a parametric approach and use an analytical flow frequency function. That is a function that can be represented using a mathematical equation. Or we go to the graphical approach, which is non-parametric or empirical. And so graphical, you're looking at frequencies and flows in a table, right? And so the graphical relationship cannot be expressed using an equation. Okay. So just a quick reminder that we're talking about whether the function in the top right-hand corner, the flow frequency function, can be described as analytical or graphical. And that will affect how those dashed lines look, right? So we're talking about the uncertainty in flow for a given frequency. How do we characterize that uncertainty in flow? And how do we sample the flow frequency function given that it is either graphical or analytical? So if we're going to think about analytical, we use a log Pearson type 3 distribution, which is a distribution that's identified using the mean, standard deviation, and skew of a series of annual maximum flows. And there is federal guidance through USGS publications, the latest being 17C, which tells us not only we should be using the log Pearson type 3 distribution to reflect the distribution of flows, we should, and we also get help on how to reflect the uncertainty about that distribution through 17C. So if you're very interested in sampling flow frequency functions, analytical flow frequency functions, that is, I'd point you to USGS bullets in 17C. So then we have graphical, that's the other option that we're talking about, where flow or stage, and we're focusing on flow here, is ordered smallest to largest, plotted against exceedance probabilities, and basically you're drawing a line between the flows to develop an empirical distribution. So the analytical can be expressed using a mathematical equation, graphical cannot. So let's look at flood conditions that, or modeling conditions that recommend one function type versus another. We want to use an analytical flow frequency function if there is unregulated streamflow data at the point of interest available, if LP3 moments can be derived using regional regression analysis or existing regional equations, or if a streamflow record can be modeled using precipitation records. So the conditions under which we can use analytical boil down to, is the stream naturally flowing? Then if the stream is naturally flowing, then there is this distribution that has been found to reflect the distribution in flows for a naturally flowing stream quite well, and that is the log Pearson type 3 distribution. If the flows are not naturally flowing, so we have a regulated channel, or these other modeling conditions that there's data available nearby, but not at the point of interest, if flow quantiles are derived, or if discharge is predicted, then we'll be using a graphical flow frequency function. So this boils down to some modeling conditions, or if the stream is not naturally flowing, if it's regulated, then we want to use a graphical flow frequency function. So they're differentiated. Economists, we might understand a simplified approach to this. If we're talking about naturally flowing streams, then we'll want to use log Pearson type 3. If we're not talking about naturally flowing streams, or streams that just cannot be modeled using a log Pearson type 3, then we're going to rely on graphical. All right. So this last bullet here, stream flows regulated, is going to bring us to another opportunity if we're talking about regulated versus unregulated mechanisms to bring in the transform function. But before I get to that, I just want to open up the floor again. Are there any questions or comments about using analytical flow frequency functions versus graphical flow frequency functions? And an extra or emphatic invitation to the engineers in the audience to add to any of the engineering discussion happening by the economist who is a pretend engineer. All right, let's continue on. So if we are working with a regulating mechanism, such as a reservoir, right? So the flows into the reservoir are naturally occurring, naturally flowing, the stream is naturally flowing, but then you have a reservoir and you're regulating the flows coming out of the reservoir. Then we have the opportunity to still reflect the variability in flow with that distribution that has been found to reflect the variability in flow quite well, and reflect uncertainty in the regulation mechanism, and that is by using the unregulated regulated transform function. So let's talk about the basics of the unregulated regulated function. So we're using this to define a relationship between unregulated and regulated flow. We can also think of this as inflow and outflow. So like inflow into a reservoir and the flows out of the reservoir. Inflows being naturally occurring, outflows being regulated. The transform relationship could be the result of a reservoir, as we've been discussing, perhaps channel routing, channel diversion. And although a graphical curve could represent an unregulated probability function, it's better to first derive an unregulated curve and then use the transform flow function to convert the unregulated curve into a regulated curve. So we're saying we want to start with a log Pearson type 3 because the stream that is upstream of the reservoir is naturally flowing. And we want to be able to take advantage of the methods that have been developed to reflect the uncertainty in that distribution that is a naturally flowing for a naturally flowing stream. But then we want to model the transformation mechanism separately and the uncertainty about that mechanism separately. And so this is kind of this is in theme with our stage frequency versus flow frequency function, right? If we can model the uncertainty about a process separately versus combining processes and reflecting the uncertainty about the joint process, we want to be able to include the uncertainties separately. And that's what using an unregulated regulated transform function allows us to do. Right, so let's look at some diagrams of this. The unregulated flow exceedance probability function is plotted here on the left. So we have unregulated discharge that is a naturally flowing stream and the annual chance of exceedance. The transform is plotted in the middle there. So we transform inflow frequency into outflow frequency. The regulated or outflow frequencies on the x-axis, unregulated or inflows on the regulated or outflows on the y-axis, unregulated or inflows on the x-axis. And we can see along that solid line versus the dashed line that the regulated discharge or the outflows are going to be lower for a certain range of unregulated discharges. And that's the idea, right? Of a reservoir or a dam that is being used for flood risk management, we want to reduce the peak flows for a given part of the probability distribution. We want to be able to reduce annual peak flows. So these two functions together will produce regulated outflows from reservoirs, and that gets us the regulated discharge function. All right, and this way we are able to include the uncertainties separately. Let's walk through an example of how this translates to risk. And this is kind of a simplified example because I'm going to assume no uncertainty in the regulation mechanism. So in the case of unregulated flow for a given event or probability of exceedance, we can identify a peak discharge from the flow exceedance probability function. The identified peak discharge corresponds to a particular stage from the stage flow or the rating curve. The identified stage corresponds to a level of damage on the stage damage function, and relating this to the level of damage, relating this level of damage to the probability of exceedance from the flow exceedance probability function identifies a probability that a level of damage is exceeded. Now we're going to bring the regulated, unregulated mechanism into the picture so that in the case of a regulated flow, say we're looking at a dam, the dam holds back flows for large events, typically lower frequency events, so that peak flows are reduced. This continues until the reservoir behind the dam would become dangerously full, at which point the releases would increase, right? So for a given flow, the stage would stay the same as nothing has changed about the channel that would alter the rating function. For a given stage, damages are the same, assuming that the dam does not encourage or discourage development. And now because the dam has decreased the frequency of certain peak stages, the damage exceedance probability function is truncated. And we can see that the truncation as the dashed red line there. So what we see is that the inflow function may be represented by the black flow exceedance probability function in the top right. And the outflow function is equal to the inflow function, except where the red dashed line breaks away from the black line, in which case the outflow function is represented by the red dashed line. And the point of this is to reflect that we want to characterize the uncertainty about the hydrology separately from the uncertainty about the transformation mechanism. And that's what we would be doing here, so that the uncertainty in damage characterize or reflects the uncertainty about those two mechanisms separately. Let's talk briefly about the uncertainty about that transformation mechanism. So inflow frequency uncertainty, the parameterized frequency function is going to represent the natural variability. So we're talking about the log Pearson type 3 distribution. And we're thinking, given a mean standard deviation in skew of annual peak flows, we have a frequency function that reflects natural variability. Now the parameterization of the frequency function, that reflects knowledge uncertainty. So do we have the mean standard deviation and skew correct? And we can reflect variation in those parameters to reflect the knowledge uncertainty. And so these two pieces, the frequency function itself and the parameterization of the frequency function, we want to be able to use the methods that have been developed for reflecting the uncertainty in a naturally flowing stream, the distribution of flows for that naturally flowing stream. Then we have regulated, unregulated uncertainty, which accounts for the volume of the event with a given flow. That involves natural variability. The information on the elevation to storage relationships involve knowledge uncertainty. And so these things are different from the components of uncertainty about the transformation mechanism are different from the uncertainty in flow. And so we want to be able to include these things separately. All right. There are alternatives to doing this, which is to go straight to a graphical flow frequency function. But the whole point here is to emphasize that that limits the ability to properly define uncertainties in flow. Okay, because we want to be able to model uncertainties separately as much as practicable. All right, any questions or comments about the regulation mechanism? All right, so I have just a couple more slides here to drive home how we're going to reflect the uncertainty. I want to spend a little bit more time on that log Pearson type 3 distribution and how we reflect uncertainty in that distribution. And I want to bring this up towards the end of this just to emphasize that the choice matters because the way that we reflect uncertainty is different if we're choosing analytical or graphical. Now, HEC-FDA version 1.4.3 implements a method for sampling the flow frequency function that is consistent with USGS Bulletin 17B. So with each iteration in 1.4.3, when we're sampling a flow frequency function, what we're doing is actually resampling the mean and standard deviation. But that's holding the skew parameter constant. We're assuming that the skew parameter is correct. And so the uncertainty in the flow frequency function only reflects uncertainty in the mean and standard deviation. Now, our forthcoming HEC-FDA version 2.0 implements a method that is consistent with USGS Bulletin 17C, so that with each iteration, a bootstrapped sample of flows are drawn from the input function, and a new distribution is fit to that sample based on the sample's mean, standard deviation, and skew. And so this approach, we are allowing for uncertainty in the mean, standard deviation, and skew. All right. So this is how we are going to, these two approaches, they're different ways to characterize those dashed lines in that top right hand figure, right? The other option, if we go to graphical, uses the less simple method. The less simple method, and you can read a little bit more about this in the technical reference. This is an approach that was developed at HEC. I think the credit largely goes to Beth Faber. Um, and if we are using the less simple method, and if using flows, we'll log transform those flows. We extend the frequency curve to almost the entire probability domain. We interpolate the quantiles and then calculate the standard error for each quantile based on equation 6 from the technical reference. So we're going to calculate the variance as a function of the exceedance probability P, the size of the sample, and the slope at the location of the quantile. Then each standard error is paired with its quantile to create an array of normal distributions. And so this fifth point is what I'd like to emphasize here, and why graphical frequency is an imperfect choice that we want to rely on only if necessary, because we're assuming that uncertainty in flow is normally distributed. Recall that normal distributions are symmetric, and so that normal distribution assumption can be considered to be less than ideal. Let's go back and look at what uncertainty in flow typically looks like. So we think about uncertainty in flow as typically being asymmetric, right? And so as you look at the diagram in the top right-hand side, you can see that there's more uncertainty in the upper confidence limit than the lower confidence limit, especially as we increase flow or decrease exceedance probability. And so that asymmetry can be modeled using the log Pearson type 3 distribution or other distributions, but reflecting uncertainty in graphical frequency functions is hard. And so we rely on the normal distribution and some assumptions that are driven through the central limit theorem. So that's how we get to uncertainty in graphical frequency functions. And again, it's not ideal. It does the job, and it does the job well if we're looking at conditions that require graphical frequency. But if not, then we don't want to impose this distributional assumption that uncertainty is normally distributed. We want to use the distribution that helps us, the distribution and the methods that have been developed for reflecting uncertainty in that distribution that match what we see in an unregulated or naturally flowing stream. All right, folks, that's all that I have on frequency functions. So we talked about using stage frequency instead of flow frequency and a rating curve. And when we would want to do that, which is a small number of situations where the hydraulic summary relationship cannot be modeled using a function that's one-to-one. That's when we'll want to go straight to stage frequency. And that occurs in situations where there's backwater or tidal conditions. So you're modeling coastal storm risk. Otherwise, we want to be able to reflect the uncertainty in flow separately from the uncertainty in stage in our distribution of expected annual damage. So we won't want to go straight to the stage frequency function. We want to use a flow frequency and a rating curve. So then, assuming we're using flow frequency, we talked about whether we want to use analytical or graphical. And if analytical, rather, if we're looking at a stream that's naturally flowing, chances are we want to use an analytical flow frequency function. If the flows are not naturally occurring, or there's another process that is influencing the flows, perhaps we would need to use graphical. The one nuance that we added in there is that if we have a transformation mechanism to model from unregulated to regulated, we would want to use a log Pearson type 3 distribution with a transform function so that we can reflect uncertainty in flow separately from the transformation mechanism. All right. Any questions, comments, concerns? I see 2 in the chat. 3, excuse me. Terrence told us that it's interesting that by rule, the analytical model has to use log Pearson type 3 with most recent risk and loss models in finance using student T, Weibull, Pareto, because the distribution tail is heavier so that it won't underestimate loss in extreme cases like the normal distribution. Now, I'd add to Terrence's comment that we are, by modeling flows, we're not going right to modeling risk, right? We're trying to model a naturally occurring process that is the variability in flow. And the engineers who've been studying this have found that log Pearson type 3 best matches the naturally occurring variability in flows. Now, Evan asked, how do graphical versus analytical distributions impact computation time? Is there a case for using graphical if compute times for analytical were prohibitive? I am going to, we'd have to study that, but my guess is that it would not impact compute times enough, one way or the other, to influence your choice of using graphical versus analytical. But we can study that and think about that further down the line, or I can get back to you on that, because it's a good question. I understand, time and money are everything if you're working under 3x3x3, and so perhaps you need to get an answer quicker. I don't think that'll be the case, but we can absolutely look at it. Andrew has a general comment. Our most recent best practices in loading curve estimates utilize stratified sampling approaches that seek to define graphically generated distributions that are samples from the tails. Thanks, Andrew. And Evan mentions that MVN always has crazy size models. It's worth considering. And I just add that, so when you have a really large model, you're talking about a really large structure inventory, right? But the uncertainty in flow is not sampled when you're computing stage damage. And so even though you may have a crazy size model with a whole lot of structures, the uncertainty in flow may not necessarily affect that compute time. And now Brian Maestri points out that this discussion emphasizes that the HEC-FDA model is not simply an economic model, but requires H&H at districts to understand how their inputs are being used to calculate damages. And yes, Brian, thanks for pointing that out. This is a conversation, right? And using HEC-FDA is an interdisciplinary collaborative effort that the engineers and economists should be working on together. And so we need to carry out that conversation as best we can, which is probably one of the hardest things that we're doing. Any other questions or comments? All right, folks. Well, if you want to learn more, you've got some resources on this slide. HEC Discourse, that's our formal tool with which to ask FDA questions if something comes up later, so you can jump on Discourse. I always enjoy hearing from the field, so please feel free to drop me an email, give me a call, find me on Teams. And if you're interested in the development of HEC-FDA version 2.0, we have 2 repositories you can follow with issue lists and everything, and the links are on this slide. All right, folks, thanks for joining. I hope that you found this webinar to be helpful. Hopefully you learned something, and look for the next quarterly HEC-FDA webinar, which we expect to in which we expect to discuss HEC-FDA version 2.0. Thanks, everybody.